Here we're going to learn about calculating average atomic mass. So grab your calculators and play our home game on calculating average atomic mass. So first off, what is average atomic mass? Well, average atomic mass is based on what we call a weighted average of the isotopes that exist for an element. Keep in mind, isotopes refers to atoms that have different amounts of neutrons. It's a weighted average, meaning we're taking into account certain percentages. It's not just a straight add up by the total number that you have and divide by that number. The number expressed, as we see here for iron, 55.85, on the periodic table, this number is expressed even though there is not an isotope of the element that actually has the mass stated on the table. So no isotope really has a mass of 55.85, even though that's the number that we use. You can think about this related to grades. We're going to use this as an example. Your average on the report card may not represent any single one grade that you've gotten or received, but that is stated as your average. It would be an example of a weighted average. So let's take this to the example looking at grades. So why not just divide by the sum of the total number? This is because this is a weighted average, so the percent abundance is taken into account that an isotope that may have a greater percentage will have a greater influence on that average. So now you're probably going, this doesn't really make a whole lot of sense. So let's relate to something you're probably a little bit more concerned about, which is grades. Think of it as a grade average where quizzes count less or a smaller percentage than a test. In this case, your grade is an example of a weighted average. So I have two examples here. In this case, the student gets the same grade on quizzes, same grade on homework, tests, lab reports, and projects. In this example, since everything is equal, if you notice our percent of final grade, everything is weighted the same, we can add up all these numbers and divide by the total. So we can add all these numbers up, divide by 5, because there's 5 different grades, and get our final average. Pretty simple. However, in this case, which is what we're going to focus on, this is a weighted average. So in this example, with the exact same grades, you need to count the weight of each. So quizzes count for 15%, homework is 10%, tests are 40, lab reports are 15, products are worth 20%. So with those same grades, we're going to take our grade, multiply by the percent. We're going to convert this to a decimal, which we're going to go over in a second. This is going to give us a number. We add all of these numbers up, and we get the average. So here you can see with this weighted average, because tests count so much and the test grade was so poor, it resulted in a lower final grade than just the straight weight, whereas everything being equal. So let's now relate this to a chemistry example. So looking here, calculating average atomic mass for boron. We're going to use this as another example. Step 1 is to find the natural percent abundance and the mass of each isotope. So here's our mass in atomic mass units, and here's the percent abundance. This information will be provided to you in some way, not expected to memorize or know the percent abundance for these different isotopes. Keep in mind that the total percent abundances should add up to 100% for all possibilities. So this is percent abundance. We need to account for all the isotopes. That'd be 100%. So now we want to convert the percent abundance to a decimal and then multiply by the mass. So how do we go about doing this? To convert the percent to a decimal, we divide by 100. So if we look at our abundance, we go back for one moment, 19.8% and 88.2% are then converted to 0.198 and 0.802. So here's our example here. 47.8% would be expressed as 0.478. We're simply moving the decimal 2 places to the left. We then want to multiply the mass, here expressed in atomic mass units, times the abundance to get a number. Once we have these numbers, we're going to go through and we're going to take the sum, will be the average of the atomic masses. We take 1.98 and add it to 8.83. So our weighted average would be 10.81, which would be the weighted average for boron. Now if you're feeling confident or you want to review that again, I want you to calculate the average atomic mass for iron. And I gave you this example. Now the problem is, in this example, I leave two things out. One the percent abundance and one's the mass. So the mass is pretty easy. We can see the isotope is 54, the mass is 54. 56, 56. So this question mark would be simply 57. The percent abundance, we have to remember what I said earlier. These all have to add up to 100. So even though I don't give you the percent or expect you to memorize it, if we add these all up and subtract from 100, we can figure out that percent. As we see here, step 1 is to fill in the gaps. 57 is the isotope number provided, and 5.80% needs to be calculated by adding up all the other percents and subtracting from 100. Continuing on, step 2 is to convert the percents to decimals. Be careful. Notice how I misspelled careful on purpose. Be careful here, because when we divide by 100, watch the placement of the decimal points. So where a lot of students get tripped up here is 0.28. We still have to move that decimal 2 places to the left, so that becomes 0.0028. Same here with 2.2%. We look back, 2.2% becomes, move the decimal 2 places, 0.0220 is our abundance. Now, just like we did previously, we're going to multiply the mass by the abundance and put the number in the right column here. Note, significant figures have been ignored for demonstration purposes. If we go over significant figures right now, we're just trying to get you to understand the basic process. So this is all of our mass times abundance, gives us our answers. Again, in red, or just the items that were left out from the original example. We add these all together, and we have our calculated weighted mass here, by simply adding up the weighted masses up to get the average atomic mass right here. This would be expressed in AMUs, or atomic mass units. Remember, there's no need to divide because the percent abundance has already been taken into account to generate our average atomic mass for iron, which would be 55.9116. You can look at a periodic table and you may not get the exact same answer, but it should be very close.